Okay, wonderful. Thank you, Berko, for inviting me. And it's good to see such a great audience. And I have the audacious title of The Future of AI. Because people always ask me, well, how can you predict the future? And I always tell them, nah, I don't think so. It's hard to predict the future. It's totally unexpected. If you want a prediction, I will say that self-driving cars will never be there, because people like driving. Back to the automotive theme, but that's all I will say about cars. So predicting the future about AI, well, what I'm going to tell you is what we see in our institute as challenges for science, because we are, of course, a scientific institute, and we have to think like, well, what can we do that the big tech companies are not doing right now? And that's not so easy, because they, of course, have their own agendas. We don't know exactly what they are, but we start thinking, well, what do we think are the important points for the future? So I'm going to talk about that mainly today. But maybe let's go back in history a little bit. This is John McCarthy, and John McCarthy actually invented the term artificial intelligence back in the 50s. And he had an idea like, well, AI will be simple. And he thought like, well, discovering the nature of intelligence is discovering like the laws of physics, like Newton's laws of intelligence. That was his image of how we should pursue AI research, and that it might take a long time to discover these laws, but once we have them, it's all crystal clear and simple. And so, of course, you can wonder, well, what is the mathematics of intelligence? And John McCarthy looked at logic, because logic is you could say, the mathematics of reasoning. So it was a plausible choice. And McCarthy actually pursued all his career using logic to do AI. And this has kept people busy for 40, 50 years until they discovered that that was the wrong road. So we've wasted 50 years to discover that logic is not the answer. Well, maybe it's still the answer. We'll get back to that, but at least... and to illustrate this, I have a problem from psychology, actually, the Linda problem. Maybe you recognize it. If you were a former student of mine, you might have seen it in my first year lectures. So there's a description of a person called Linda. You can sort of read it here. She is single, outspoken, did philosophy, considered discrimination, etc. And then there's a question, what is more plausible? Is she a bank teller or a bank teller and active in the feminist movement? So who thinks answer 1 is correct? And votes for 2? A couple of them too. So you're a pretty rational audience, because if you follow the laws of probability, then answer 1 is correct, because, and this is called the conjunction fallacy, that if you look for the probability that 2 things are true at the same time, that's always less probable than one of them is true. And this is a problem by Daniel Kahneman, the Nobel Prize winner, mainly known for this book, Thinking Fast and Slow. Maybe it's in your bookcase and you've never read it. That's usually with these kind of books. It's actually a good read, but if you haven't read it, pick it up still. But the interesting thing is, who says that answer 1 is correct? Why not answer 2? Well, of course, you say like, yeah, it's the laws of probability, etc. But who says we are governed by the laws of probability? Because answer 2 is much better fit, right? Fits the person much better. So I'm not telling you like Kahneman did, like, yeah, you're wrong. No, answer 2 might be as valid as answer 1. And if you look at present day AI, so answer 1 is McCarthy. Answer 2 is present day AI. Because it's about recognizing patterns, finding fits. And that means that maybe we went to the other side a bit too much. So here is, I have also AI-generated pictures, and as you will see in my presentation, they're all wrong. So here is one. If you ask one of these picture generators, give me an industry board on artificial intelligence, you get a bunch of white males in gray suits, with ridiculous language in the background, and there's only one woman on the panel, but she has a laptop open, so she's probably there to take notes. So, of course, we all know about bias, but it's hard to ban bias. There's not an easy way to get rid of bias, and that is because we forgot about the logic. We forgot about the reasoning. So how do we get that back? Now let's move a little bit to my institute. We are the Benoei Institute. We have this blue building at the campus on Zernike, also called the Benoei Borg. And we have right now about 700 students of AI. So for those of you who were former students of mine, we have a lot more students right now. Which also means quite a capacity to help you in projects. So if you need an intern or someone who's doing a project with you, then come to us and also meet former student of us, Marleen Schippers, who's now our coordinator for our external relations. So if you have, say like I have a nice project, I could use an AI student to help me with that, contact Marleen, because we're eager to collaborate with you on giving you a student to do the interesting AI work. So back to the future of AI. This is again another AI-generated image. If you ask for the future of AI, and you get this sort of scary image. I don't know whether this is the kind of future we want. So for me, well, if you look at what we are doing in the Institute, of course we do a lot of things, because if you have an educational program, and by the way, we are the #1 program in the Netherlands. We're always #1 in the keuzegids hoger onderwijs, so we do produce, at least students are very satisfied about us, and so is the keuzegids hoger onderwijs. I think we produce students who do a good job in industry. So we try to cover all the topics in AI within our program. Of course, we are also thinking ahead, like, well, where can we make a difference? And I would like to highlight 3 things today. The first of all is bring reasoning back. I sort of already started that conversation with you. And the second one is hardware for AI. And the third one is human-AI collaboration. And I'll go into each of these separately. Now, if you are a student of computer science and you've done your computer architecture, you may have encountered a diagram like this. It's called the stack, and it's about how we build computers. So from the bottom up, we start with transistors, and from these transistors, we build logical circuits, we build memories, we build basic circuits. At some point we have assembly language, and at the top there is a higher level programming language, and maybe on top, maybe level 6 is now large language models who generate this problem-oriented language. Of course, this idea has been around a lot, but what you see here is that even something as engineered as a computer requires many levels of abstraction in order to fully understand it. Now, of course, in computers, it's designed in this way, so every level in this stack can be understood from the level below. And of course, this is not just in engineering the case, it's also the case in nature. If we look at science, we start with physics and subatomic particles. At some point we move to chemistry and to biology, and ideally all these levels sort of are connected to one another. And if you connect all the dots, and of course this is also one of the goals of science, if we connect all the dots, we have a full understanding of how life comes into being. So why do we think intelligence is more simple than this? Because intelligence is one of the most complicated things in the universe. At least that's what I dare say. So we are also looking at how can you analyze intelligence and artificial intelligence as, you could say, a stack like that. And then not in a fully designed stack, but something intermediate between design and sort of experimental research where we investigate nature. So here's our stack. Now, I'm not going to explain this whole stack to you, but it has several components in it where we say, like, well, we have the smaller units, so neurons and neural networks, and we gradually try to build up to systems that can perform arbitrary tasks. So if we map sort of the current approaches to, or the old approach of AI, so good old-fashioned AI, started at the top and say, like, well, can we design the general rules of reasoning? Whereas now we're doing the bottom-up approach. We start with clusters of neurons, and we feed them with data, and we hope to gradually build up intelligence from that. But our goal is also to say, like, well, we have to look at the middle bits and see, can we learn something? Also from neuroscience and what we know about human intelligence in order to maybe speed up this process. Because as we all know, for generative AI, you need to do a huge amount of training. You need to spend a lot of energy in order to get the results that we get. So the fact that generative AI can still do a reasonable job, even at reasoning tasks, means that they're just overloaded with data. So it can, it's sort of someone once told me, yeah, sort of large language, it's like an intelligent lookup table. It's not real intelligence. So can we find things in the middle here that maybe allow us to provide faster AI and also to not require this huge amount of training and learning, because we're running into the limits there. Now, about running into the limits, it's also the case that if you look at our computer hardware, I showed you the stack, our computer hardware is also based on the old logic idea. So our current computers are no longer compatible with what we want to do with them, with AI. Of course, we're still able to simulate neural networks on computers, but it's super inefficient. And of course, we discovered GPUs, which makes it a little bit better, but it's still inefficient. So we need a new kind of hardware. We need the hardware of the future. And this will be a big job, because our current computers are so well developed that if we start from scratch and building new computers, we also have to develop the whole new computer stack once again. So if we look at McCullochs and Pitts, these are the neurons that make up all our big neural networks. Maybe with a little bit of a different transition function, but this is the basic unit for most of machine learning, most of AI that we now have. And of course we can say, like, well, can't we build these neurons in hardware instead of simulating them on hardware? And this is called neuromorphic computing. And it's already, the big chip makers are already looking at that. So Intel has one, IBM has one, there's several others. In the Human Brain Project also produced one called Spinnaker. But the way they are constructed are a bit like this. So a sort of very simple diagram. They said, like, well, let's build a sort of digital circuit that simulates a neuron. So we're still simulating, which means that the weights in the neuron are sort of stored in registers. Of course, the register is 32 bits, so it's still a whole bunch of zeros and ones, and we finally have to do a sort of arithmetic unit. So we have to build even sort of tiny computer cores and link them together. Of course, this is already a big step forward, but we're not there yet, because this gives us a modest increase in efficiency, and we want a huge leap in efficiency, because if you look at IBM's True North, this is still something like 2,000 transistors to build a single neuron. And we don't want 2,000 transistors for a single neuron, we just want a handful of components. So the next step we're looking at is, like, well, can't we build neurons in sort of using analog electronics? Instead of doing this all digital, if we want to do multiplication of weights and adding them up, we can also do that with analog circuits. And then you get something like this. However, there's one problem. In this circuit, there are components that don't actually exist. And it's those two guys. And those are called, well, we call them memristors. And they are resistors that have a variable resistance, and their resistance is based on their past. So it's a resistor with a memory. That's the component, the magical component to allow this to work. And we're doing research on this. We have a center at the University of Groningen called Pygrunn. It's a collaboration between my institute, so computer science, mathematics, and AI, and the physics department, the Material Science Institute, the Zennik Institute. So they built they're investigating the new electronics with new materials. And here is a diagram of one of the prototypes that we have. Actually, it's one that I did a project on. And this is a memristor, based off materials that I know very little about, because I'm not a physicist. But it has the property that it can have different levels of resistance based on its past. So a low resistance state or a high resistance state, and states in between. And this means that we have now in our hands a potential component for such a new computer. But of course, we have to find the right components. We try many different components, because some of them only operate at a minus 30 degrees. That's not good. Some of them operate only with 50 volts. That's also not good. Some of them lose their memory in a couple of hours. That's also not good. So there's a lot of work to do on the material side to get the ideal component. But once we have that, we also have to think about how to build a new kind of computer architecture from there. And one of the things that we also are looking at is how do we make these things energy efficient? Now we know about the brain, that the brain only uses 20 to 25 watts of energy. Now if we can mimic that in our future computers, then we can do a lot more with AI. Now one of the things that we need for that is to say like, well, maybe we have to say goodbye to our old zeros and ones that we have in our computers. Arrow said like, well, we're looking at analog components, but also if you look at the brain, is how do brain cells communicate with one another? They communicate with this, very small spikes of activation, spike trains. So we're also looking at, well, how can we build a different kind of neural network, not based on activation values, but on activation patterns, where there's a pattern of spikes that controls the information flow. Because for our future hardware, this is maybe the better energy efficient solution. Once we have these sort of new materials, we can also start thinking about how do we do computation with it. So we might have some neuromorphic material, and this can be, we're looking at very different options, and of course the physics people are much better at explaining this, but they look at spintronics and magnetics and, no, it's not my time yet. But you can sort of say like, well, whatever this material is doing, we can map it onto a vector. And of course we know that vectors are embeddings and that are used in large language models, but also in other machine learning situations. But if we can make these materials in such a way that they do the computation for us, so they can do the matrix multiplication or the mapping of the multiplication of a vector and a matrix in an analog fashion, then we're doing a lot more efficient computation. And this is what we are looking at within our institute together in this Cognigram collaboration. Now this will not be done in 5 years. It's further in the future. We're collaborating with ASML, and ASML says like, yeah, we find this interesting, but we're not ready for it yet. But we keep a close eye on you. Once you get real results, we will jump in. And this is exactly what the academics are for, right? To do the more future-oriented thing where the industry doesn't dare to go yet. Okay, final topic, human-AI collaboration. We're looking at many different aspects of human-AI collaboration. I just want to mention 2 of them. One thing that we do a lot of research in is theory of mind. If you want to collaborate with AI, then AI has an understanding of you. It has to have what we call a theory of mind. It has to have an idea what you want, what your knowledge level is, and it has to be able to reason about that. Now, unfortunately, current AI is not very good at theory of mind, and this is something that we want to improve. So the classical thing for theory of mind is a Sally-Ann problem. It's sort of depicted here in the picture. So Sally, there's a basket and there's a box, and Sally and Anne are in a room. Sally puts a red ball in a basket. Anne goes away. No, Sally goes away, and then Anne takes the ball and puts it in a different location in the box, and then Sally comes back, and then the question is, where will she look for the ball? And this is a problem that they give to young children. Very young children make a mistake here because they will point at the actual location of the ball. But once they grow a little bit older, they know, okay, it's there. Now, if you ask this to ChatGPT now, it gives the correct answer because it has read all the literature on the Sally-Ann problem. But the early version actually had read about the literature, but still made a mistake. So I'm not sure whether you can read this, but here's the problem. And then ChatGPT said, Sally will look for the ball in the box. And then you ask, well, what's the Sally-Ann test? And it gives you a perfect definition, a perfect explanation. This is sort of interesting because it's the sort of reverse of that we say, like, well, we want AI to explain its actions. And it took the sort of wrong action, but it can explain what the right action is. So it's sort of funny. But again, if you ask it now, and I ask it actually a more complicated problem that we used sort of second order theory of mind a couple of years ago, and I asked it today, I just wanted to check with ChatGPT, and it gave the correct answer, but it also gave a reference to my PhD student's paper. So it's again, so eventually ChatGPT will pick up on any sort of thing, example like this, but not because it has mastered the reasoning, but because it's just this big lookup table. So this is still a challenge to have actual theory of mind, because in real life situations it's different every time. So lookup doesn't work there. Okay, I see I'm at minus 12 seconds. Final thing is, one of the things we're looking at is how can we use it in education, AI? Because the challenge in education, and this is what we see in university, that students fail on courses because they miss certain knowledge. So if you have a student who has mastered some sort of basic arithmetic like this, then choosing the right material is very important, because we can give them more of the same, or you can give them something really complicated. But if you give them more of the same, they'll get bored. If you give them something too complicated, they will get frustrated. So you have to give them something that is just right. And this is a real challenge, because we don't know what's in the student's head. We don't even know how students differ in what they have in their heads. And this is one of the projects that we're working on, where we say, like, well, we want to see, first of all, we want to discover what's in the knowledge. What is actually the skills that the student need? Because we don't actually really know what education does or what it takes. And then we want to create a sort of personalized education for that particular student. Now here is a sort of little interface that we used for that. This is for MBO students at the Alpha College here in Groningen, where we dissected an arithmetic course taught by Noordhoff Publishers. And we turned out that the learning goals, or at least the skills where the students differed, were quite different from what Noordhoff thought they were teaching. And we managed to have a personalized teaching system for those students that quite improved their performance. Well, no time to go into big details. Now, here a final AI-generated image. I asked it to make a picture of the expression, is the glass half full or half empty? You can see that this image generator is also not very good at idioms, because it just generated a glass that was, well, slightly over half full. Not the sort of idea of the idiom. So I would say it's both. It's fantastic what we can do with AI nowadays. I wouldn't have expected, if you would ask for a prediction 5 years ago, that we would be at the stage where we're now. But it's also still half empty. There's still a lot to do. And I hope that you will all be part of that, because I think it's a great enterprise. AI has always fascinated me. I spent, in my second year of computer science, I discovered I wanted to pursue AI. Computer science wasn't at that time not interested in AI, but I've persisted, so now I'm here. And I see it's great to have such a great audience, and also to have so many former students. That's really great. Again, contact Marleen if you want to do a project with us, and otherwise, thank you for your attention.
Thank you very much.